It's Monday morning, and we are going to finish your notes on vectors in the plane. We are on your number 20 in your notes, and I know it's been several days since we've had class, but the last big thing we discussed was how you can write a vector in component form. That's what we're going to use, okay? Now remember, the theta that we use is going to be a theta that we would put in our calculator, so it will be an angle in standard position. Let's remember what a bearing is. We talked about a bearing last week. Remember, a bearing is measured from due north clockwise. So if you are given that an airplane is flying at a bearing of 247 degrees, what quadrant would that plane be flying into? $90, 180. Going another full quadrant would be 270, and it's not that much. So it's flying right here. That's not an angle we can put in our calculator. We need this angle right here. How are we going to figure out that red angle? Yep, you're going to find that reference angle. Now, you can do this a couple ways. You can do 270 minus 247 to find that little piece. What is that little piece? That's 23 degrees. So what's this piece? Oh, so this is not 20. This is not 23. This is 23. Okay. What is the red angle then? Because it's 180 plus 23. So we would need to use an angle of 203 when we write it here, okay? Now, let's look at an example. Look at your number 22 in your notes. Oh, no, we got to talk about 21 for just a second. This is, y'all hush, bless you. See if we can get this to go bye-bye. If I take this little pattern right here, you'll notice that both of those components, the horizontal and vertical components, have magnitude V in it. If I consider that to be like a greatest common factor sort of, and I factored it out, you could think of it like this. Where you could think of magnitude V as a scalar. Now, I want you to look at this. If I divide both sides by magnitude V, I want you to look at what we've got. And this is your number 21 in your notes. Now you think, well, so what? That doesn't mean crap to me. Please notice your horizontal component and your vertical component. Yes? Now, do you remember how to find magnitude when you have your vectoring component form? Pythagorean theorem. It's the horizontal component squared plus the vertical component squared, and then take the square root. Yes? Well, let's do it. Let's find the magnitude of this vector right here. Well, it's the square root of the horizontal component squared plus the vertical component squared. Holy mackerel, that's 1. Oh my goodness. Ladies and gentlemen, this right here is a vector of magnitude 1. Oh my goodness, that's a unit vector. Question? Any vector divided by the magnitude of that vector will give you a vector of length 1, but it's going to be going in the same direction as the original vector because they've got the same angle. So if you ever need a vector that has a magnitude of 1, then this is what you'll do. Now let's go to your number 22. Find the components of the vector v with direction angle 115 degrees and magnitude 6. When it says direction angle, that's already telling you it's in standard position. Let's write that vector. Now remember, we're going to write it just like this. The magnitude of the vector is 6. Direction angle is 115 degrees. That's the horizontal component, and the vertical component. That's all you have to do to write a vector. That's it. Nothing else to it. This tells you the horizontal component, and this tells you the vertical component. Okay? Now, let's look at your number 23. This is a big piece of what you're going to have to do, okay, in your application problems, which we will start right after we do number 23. So please look at number 23, part A. It says find the magnitude and the direction angle of each vector. We are given a vector u whose components are 3, 2. Now we're going to find the magnitude and we're going to find the direction angle. Okay? I'm just going to tell you when I do these, it is just extremely helpful to me if I draw a little sketch. We're going to put these vectors in as a position vector, meaning we're going to start it at the origin. So if I start this vector at the origin, this means I'm going to go what directions and how many? Good. I'm going to go right 3 and up 2. So this vector's head would be right there. You can do the magnitude in your head because if you look at it this way as a right triangle, Pythagorean theorem, you know that this is 3, this is 2. What's the magnitude? Square root of 13. Now you say, well, do I really have to draw the picture? Nope. You can say the magnitude of vector u is the square root of the horizontal component squared plus the vertical component squared, and that gives you the square root of 13. You don't have to draw the picture. The reason I draw the picture is not for the magnitude, it's for the direction. It just helps me in my head. Now, so we got to find the direction. What direction is this thing going? I need that angle right there. Bless you. I need that angle. Do I know enough to find that angle? What could I do to find it? Which one? Which one of those trig things? Tangent. Because tangent is what over what? And I know opposite and adjacent for that angle, don't I? So tangent theta equals what over what? There you go. How do I get theta by itself? So tangent inverse of 2/3 equals theta. Make sure you are in degree mode on your calculator and run that. Let's see what are you getting? Would help if you turned it on. Oh. Is that angle one that makes sense in this picture? Yes. So we've got our magnitude and we've got our direction angle. So what we're going to do is we are going to combine what we're doing right here and what we did right somewhere. I guess I lost it. Maybe I erased it. No, right here. We're going to combine those two things to actually work application problems. So let's look real quick at B, and then we will go to the good stuff. Ma'am. Let's look at part B. Vector V is -2, -5. We need to find its magnitude and its direction. Let's draw a position vector. What quadrant is that thing going into? All right, -2, -5. So left 2, down 5, right here. What's its magnitude? Square root of 29. So magnitude of V, square root of 29. -2, -5. Remember, I need this angle right here. But what I've got to do is go find the reference angle first. How am I going to find it? Tangent inverse? Good. Tangent inverse of -5 over -2? What do you get? 68 point what? Okay. Yep. Now here's the deal. That big red angle is not 68.199 degrees. That's right. This angle is in quadrant 1. That angle sits right here. Go back to geometry. One of the few things I really, really loved about geometry was doing this kind of stuff right here. What is the relationship between this angle and this angle right here? Why are they congruent? They're vertical angles. Okay, they're vertical angles. So, how do I get the big red angle? Good. So, now listen here. Do not write plus 180 right here. That's not right, because you are implying that the inverse tangent of 5/2 is this whole big thing. But it's not. So you're just going to go down here and say the direction angle. No. DA means district attorney. What's the direction angle? All right. That's it. Degrees. Don't forget your degrees. Number 24, we finally get to the good part. Why do we need vectors? You are driving to Taneytown, and the wind is coming out of the out of the west. Why are you going to go faster? Good, because the wind is pushing you. So you are going to go faster than what your speed gauge tells you. Thank you. What your speedometer tells you. Speed gauge. If the wind is coming out of the east, so it's blowing toward the west, and you're driving to Taneytown, it's going to be a little harder because the wind is pushing against you. So even though your speedometer says 65, which it shouldn't say more than that, right? Shh. You're not going to really be going quite that fast, are you? Because most of the winds are predominantly one direction. Really? One direction. All right. Go to your textbook. All right. So you are on a plane. Now, there are some terms you need to know. We are going to be on page 465. 465. Now, the airspeed means there's no wind. Now, so if we take what the plane is doing without wind plus the speed and direction of the wind itself, then we get what the plane is actually doing with the wind blowing on it, which is called the ground speed. Don't ask me. These are just the words that they use. I don't know. Honey, I don't know why they're called this. They just are. So we just go with it, okay? So what you have to do is you have to find two of those three vectors. You have to be given enough information to write two of those three vectors, and then you can find the other one. Typically, we will be given the airspeed and the wind, and then we'll have to find the ground speed, all right? Mm-hmm. No. Now, we also will be doing a problem involving boat. So even if we talk a boat. So it would be like this: the speed with no current plus the current equals, they don't have special names that I know of, speed with the current. That's very clever, right? Innovative, yeah. So that's what we're looking at. There are no special words, so yeah, I just wrote down what made sense to me. All right. Oh, shut up. 43. We're going to do number 43 in your textbook on page 465. Maybe. Listen, I changed my mind on the problems I wanted to do. Now you should still have some room on the back. So we're going to work number 43. Now let's have a look. An airplane. I'm waiting for everybody to be listening because they aren't. An airplane is flying on a compass heading or bearing of 340 degrees at 325 miles an hour. A wind is blowing with a bearing of 320 degrees at 40 miles an hour. Now, we're not going to consider part A and part B. We're just going to work the problem, which is to find part B. What is the actual ground speed and direction of the plane? So, what I'm going to do, and I would really encourage you to do this, is just over on the side, draw. Now it says the airplane is flying on a bearing of 340 degrees at 325 miles an hour. We can't use 340 degrees because that's a bearing. We got to figure out what angle we use. Where is a bearing of 340 degrees? Where? It's 180, 270. So it's up in here. I need this angle. Why is it 110? Good, because this is 20 degrees. So the red angle is 110. So the airspeed We're just writing a vector for the air. Magnitude times cosine of theta. Magnitude times the sine. I'll probably put that in a bad place there. Times the sine of theta. We've just written a vector for the plane with no wind pushing on it. Do you understand where that came from? Everybody okay there? Okay. There is wind. We know there's wind. There's wind. Life is good. There's wind. There's always wind. Huh? Well, how about that? Air. That is the vector for the plane with no wind pushing on it. So let's just call it that. Let me stick this. So there's the plane. Now, we need a vector for the wind. What's it say about the wind? It says the wind is blowing with a bearing of 320 at 40 miles an hour. A bearing of 320. What's that angle? This piece is 40, so this piece is 130. So I've got a magnitude of 40. So I've got 40 cosine 130. What the crap is that? Cosine 130, 40 sine 130. Sorry? Yes, speed is magnitude. Now look, I've got the plane is going this way. The wind is going this way. Why did I make the wind's vector shorter? Because it's not anywhere near as fast. Now, it will affect it, but we got to decide how much. Now, do you remember when you add vectors, when we did it on paper? If we wanted to add the wind's vector to the plane's vector, we would add it up here, right? So the plane really is going like that. Now, so we want to find the ground speed and direction. Well, all we're going to do is add those two vectors together. Now, here's what you're going to do. You're going to take your calculator. Ground. The horizontal component of that green vector is this plus this. On your calculator, I want you to add those and do not erase what you get. Give me a number. Negative what? I'm sorry. 0.87? You better be in degree mode. Now, you don't lose that. You are going to store the exact answer you got there. You're going to store it in A. We are not going to use rounded values. Now you're going to do exactly the same thing for the vertical component. Vertical plus vertical, and get your vertical component. Question?
Sorry, can you do like a quick 2-second review on how to store this?
How to store. Stella, what number did you get here? Is this a good number for the vertical component?
Yes.
I want you to store that in B. Ladies and gentlemen, now we have the horizontal and vertical components. How do I find the speed? The Pythagorean theorem. So the Pythagorean theorem, all you're going to have to do on your calculator is this. That's all you have to do. So the magnitude of the vector (362.85). What unit? Miles per hour. Did the wind speed the plane up? A little bit. Is that logical based on our picture? Yes, it is logical because it's sort of a tailwind. Now let's find the direction angle. How do we find the direction angle? Tangent inverse of opposite over adjacent. But the opposite is the vertical piece, and the adjacent is the horizontal piece. So it's tangent inverse of B over A. Is that an angle that's acceptable? Is that an angle that's in quadrant 2? Where is that? That's in quadrant 4, isn't it? Yeah, yeah. That's down here, negative 67 point whatever. I need to throw it into quadrant 2. So how am I going to do it? Yeah. To throw it up there, I'm going to do 180. I'm going to add 180 to that. I'm going to go counterclockwise, which is in the positive direction, which means add. What do you get? Let's go 3 decimal places.
161.
Degrees. Don't forget your degree symbol. Now, this is where you have to be careful. Please look at the question. Find the direction of the plane. If it's given in a bearing, you got to answer in a bearing. That's not a bearing. That angle that we have got is this angle right here. We need this angle right here. Well, I don't know. Can I? What am I going to do? Why do you want to subtract 360? Well, subtract 270? What's that angle right there? If that blue angle I drew is 112 point something, then what's that little green angle?
22.
Yeah, because it's 112 minus 90. So this is 22 point whatever. So how do I find the red angle?
You do 360 minus 22.
I do 360 minus this 22 point, and that'll be your bearing. What is it, 337.84? Yeah. You're going to write a sentence. You're going to say the plane's ground speed is 362 point whatever miles per hour, and the plane's actual bearing is 300 and what, 337 you said? 337 point something? The bearing angle is the red angle. I took the blue angle and figured out what this little piece was right here, which is the 112 minus 90. Well, the red angle is the entire circle except for that. So 360 minus that piece. Okay? Uh-huh. Well, it's 22 point something something. Yeah. So, okay. Use this. Okay. Do you have questions? Okay, we're going to do a problem about a salmon. Now this problem is in your book on page 463. So go backwards. 463, and it's in the blue box. 463. Go the other way. There you go. It's in the blue box. Now, if you would, cover up the stuff that's below the picture because that's the answer. And I'd rather you not be looking at the answer while you're working the problem. 463 in the blue box. Okay, has everybody got the blue box? All right. During one part of its migration, a salmon is swimming at 6 miles an hour, and the current is flowing downstream at 3 miles an hour at an angle of 7 degrees. How fast is the salmon moving upstream? Please notice this does not ask us for a bearing because you could set up the problem where the river is up and down on your paper or left and right on your paper. So depending on that is going to determine your angle. So the speed though is going to be the same regardless of how you set up the picture. So I'm going to make my river. There's my river. Now, the salmon is swimming upstream. Now, what we're going to do is we're going to consider that the river is due north-south, so that salmon is swimming due north. That information that says he is swimming at 6 miles an hour, is that with the current or without the current? Without. So we need a vector without the current. So let's write a vector without the current. Magnitude is 6. Cosine of. We're going to be letting that salmon be swimming due north. Due north would be 90 degrees. That's the horizontal component. What's the vertical component? There you go. Now the nice thing is we know cosine and sine of 90 degrees. What's the cosine of 90 degrees? 0. So this vector really is a very simple vector. 0, 6 times 1. Now let's write a vector for the current itself. Now it says the current is flowing downstream at 3 miles an hour at an angle of 7 degrees. It does not tell us if the 7-degree angle is this way or if it's this way, and it doesn't matter because it's not asking for a direction. You can do it either way. I'm going to let it go this way. When it says at an angle of 7 degrees, it means that little red angle right there is 7 degrees. Now, I just wrote those vectors, excuse me, I just drew those vectors like I was adding the two vectors because I started the current where the salmon's ended. I could have drawn them both in standard position though and made the current go this way. Yes? You with me? Now there's a reason I drew it like that. I think it will help you to get your angle right. Now, what's the magnitude for the current? Cosine of. Now, we got to figure out what this angle is. Remember, it's going to be an angle in standard position. So what I need is this angle right here. That green dotted in is the X and Y axes. So what's that blue angle? If this little piece right here is 7 degrees. Say again? I could do this. I could do negative 83 degrees. Couldn't I? Because it's going in the clockwise direction, 83 degrees. So I could do it this way, which would be absolutely fine. 3 sine of negative 83 degrees. What other angle could I have used? What angle would that red one be? 277. Those 277 and negative 83 are coterminal, so they will have the same sine and cosine, so it doesn't matter which one I use. Now, salmon with the current. What's my horizontal piece going to be? Well, it's going to be this plus this. Run it on your calculator, get us a number. Point, is that what you said? 0.36? 0.366. Store that in A. Your vertical component is this plus this. Give me a number. 3.022. Store that in B. The only thing this was asking was, what is the salmon's speed with the current pushing on him? How do we find that? Pythagorean theorem. So the magnitude of that salmon is the square root of A squared plus B squared. What number are you getting here? 3.04? 3.04 what? So even though that fish is swimming at 6 miles an hour, he's only making this kind of progress. 3.04 miles per hour. Why is his speed not cut exactly in half? That's right, because the angle is not straight head on. There's a little bit of an angle. What if it was? Then his actual speed with the current would have been 3 miles an hour. Because it would have been the speed he's trying to do, minus the current. Guys, all of these problems, you're going to do the same way. Now, you may see a problem where, for instance, it might give you the salmon without the current and the salmon with the current and ask you what the current was. But you'll be given enough information to find 2 of the vectors, then you got to go find the other one. Okay? These are cool. I really like doing these problems. So, your assignment. Oh, snap. We need to look at one other thing. We do. Go to page 465. Yeah, we got to look at one other thing. Let's look at number 49. I forgot about this one. This is a physics problem. This is about forces. Not horses, forces. because I know you, Gus. Find the direction and magnitude of the resultant force. So look at number 49. A force of 50 pounds acts on an object at an angle of 45 degrees. A second force of 75 pounds acts on the object at an angle of minus 30 degrees. What is the direction and magnitude of the resultant? Question. Yeah, force, we're just going to substitute for speed. That's exactly right. Draw you a little picture. We're going to draw two forces in standard position. It says the first force of 50 pounds acts on an object at an angle of 45 degrees. So we're going to draw a vector, 45 degrees, and the force is 50 pounds. Then it says there's a second force of 75 pounds that acts on the object at an angle of minus 30 degrees. Question 1, why did I draw the red vector longer than the purple vector? That's right, it has more force. It is stronger.
Why is it on the x-axis, not like on the vertical? Isn't it started due north?
Only if it's a bearing. Only if it's a bearing. Forces, we're able to just put as just regular old angles. Now, this is going to seem like a really weird example, but let's say that Kenya is standing right here. Kenya. And, well, you should. And Kenya's got a rope around her waist, okay? Actually, she got two. This is Gus. Gus is pulling at 50 pounds of force this direction. And Jael is pulling on this rope at a force of 75 pounds. Sorry, Gus. You had it coming. Now, here's the question. Where is Kenya going to go? Well, you think a little bit more towards Jael? Why would she be going a little more towards Jael? Okay, so that's what we're going to figure out. They are pulling at different angles, absolutely.
So what if she just goes straight?
Well, let's see. Maybe she does. Maybe the angle we come out with is 0 degrees. Let's see. Now, here's what we're going to do. We're going to call this force 1, so we're going to write a vector for force 1. Force 1, let's write the vector. Magnitude, so it's 50 cosine 45 degrees, 50 sine 45 degrees. So that's Gus. Jael is force 2. What is the vector to represent Jael? 75. I can use minus 30 degrees if I want to, that's fine. And 75 sine of minus 30 degrees. Now, to figure out where Kenya actually gets pulled, what are we going to do with those two vectors? Add them together. So, F1 plus F2. Here's what I want you to do. I'm not going to talk you through all of this. I want you to find find the horizontal component, store it in A. I want you to find the vertical component and store it in B. Then I want you to find the magnitude and the direction. No, I do not want to delete this recording. Okay, I'm just working this kind of by myself here. I got negative 2.145. Okay. We're going to store that in B. Are you getting these numbers? What is the resultant? What are you getting as a resultant? Question. What is the unit for this force? Pounds. Now, here's my next question. Does this number, a little over 100, make sense? Does it make sense that the force with which Kenya's being pulled with is a little bit bigger than these?
Yes.
Because why? And because they're kind of pulling in a similar direction, they're both kind of pulling this way. Now, what about the angle? What'd you get for an angle? You win? What'd you get for an angle? I got negative 1.225. Yeah. How do you do that? Tangent inverse of B over A. Is that reasonable here? Just a teensy bit in Jael's direction.
I won in a call.
Question. Why is it so little in her direction? Because the angle for Gus was bigger. Yeah, so she had more of an angle to counter. But it does nevertheless go in her direction. Okay, so Kenya would be pulled in this direction with a force of a little over 100 pounds. All right. There's a problem. Number 48 is like this problem, except it's for whatever reason, two people have a puppy. Two people have leashes on a puppy. Okay, so that's what number 48 is about. Now, your assignment. Make sure I have. Oh, you choose to accept it. Your assignment is textbook, page 465.
We're gonna pull apart these puppies their own part? Is that what we're doing?
Oh. Number 44 and number 48, plus a handout I'm getting ready to put in your hands. Do them